question at hand concerns whether 4 200-amp main circuit breakers comply with the National Electrical Code (NEC) requirements for secondary overcurrent protection for a 225 kVA transformer with a 480 volts to 208/120 volts 3-phase 4-wire configuration. The secondary conductors consist of two sets of 500 MCM spliced in a trough to 4/0 per phase, feeding these 4 200-amp main circuit breaker panels. According to the NEC, secondary overcurrent protection for transformers must have a rating not exceeding 125% of the transformer's secondary current rating. Let's calculate the transformer's secondary current rating. The formula is secondary current equals transformer kVA divided by secondary voltage multiplied by the square root of 3. Plugging in the values, we have secondary current equals 225 kVA divided by 208 volts multiplied by the square root of 3, which calculates to approximately 644 amps. Therefore, the overcurrent protection limit for the secondary is 125% of 644 amps. Multiplying 644 amps by 1.25, we arrive at 805 amps. In this scenario, each of the main circuit breakers is rated at 200 amps. Since 200 amps is substantially below the calculated overcurrent protection limit of 805 amps, these 200 amp main circuit breakers, as currently configured, do not provide adequate overcurrent protection for the transformer secondary according to the NEC. To achieve compliance with the NEC requirements, the overcurrent protection devices utilized for the transformer secondary must have a rating that does not exceed 805 amps. There are a couple of potential ways to achieve this. Firstly, one could implement main circuit breakers with a higher amperage rating. For instance, a single circuit breaker rated at 400 amps, or even a single breaker at or below the 805 amp limit could be used. Secondly, fuses or circuit breakers, provided they are rated at or below 805 amps, could be employed. It's crucial to consult the NEC and local regulations for specific requirements and approved methods in your jurisdiction. The NEC provides tables and guidelines for selecting appropriate overcurrent protection devices based on transformer size, conductor ampacity, and other relevant factors. Here's a breakdown of the key considerations. Firstly, calculate the transformer's secondary current. Use the formula secondary current equals transformer kVA divided by secondary voltage times the square root of 3. Ensure that you convert kVA to volt-amps by multiplying by 1000. Secondly, determine the maximum allowable overcurrent protection. Multiply the secondary current by 125%, or 1.25. This is the maximum amperage rating for the overcurrent protection device protecting the transformer secondary conductors. Thirdly, select the appropriate overcurrent protection device. Choose a fuse or circuit breaker with an amperage rating that is less than or equal to the maximum allowable overcurrent protection calculated in the previous step. Fourthly, verify conductor ampacity. Ensure that the secondary conductors have an ampacity rating that is at least equal to the transformer's secondary current and that the overcurrent protection device protects these conductors. Consult NEC Table 310.15 for conductor ampacity ratings based on conductor size, insulation type, and installation conditions. Fifthly, consider coordination. If there are multiple overcurrent protection devices in the system, such as upstream and downstream breakers, consider coordination to ensure that the downstream devices trip before the upstream devices in the event of a fault. This helps to isolate the fault and minimize disruption to the electrical system. Sixthly, local codes and regulations. Always comply with local electrical codes and regulations which may have additional requirements or restrictions beyond the NEC. Consult with a qualified electrical inspector or engineer to ensure compliance. Seventhly, documentation. Maintain accurate documentation of all calculations, equipment specifications, and installation details for future reference and inspection purposes. It is very important to note that the NEC permits the next higher standard overcurrent device in certain situations, as outlined in NEC Section 240.4b. If the calculated overcurrent protection value does not correspond to a standard fuse or circuit breaker size, you may be permitted to use the next highest standard size, provided certain conditions are met, such as the ampacity of the conductors being protected. However, it is crucial to carefully review the NEC requirements and consult with a qualified electrician or engineer to ensure that this exception is applied correctly and safely. Also, be aware of transformer primary protection requirements. While this discussion primarily focuses on secondary overcurrent protection, it is equally important to ensure that the transformer primary side is adequately protected. The NEC has specific requirements for primary overcurrent protection based on the transformer's primary voltage and current rating. Understanding transformer impedance is important. Transformer impedance, expressed as a percentage, indicates the transformer's opposition to current flow. This impedance plays a crucial role in determining fault current levels. A lower impedance transformer will allow for higher fault currents, requiring overcurrent protection devices with higher interrupting ratings. Consider the available fault current at the transformer secondary. This is the maximum current that could flow during a short circuit condition. The overcurrent protection devices must have an interrupting rating sufficient to safely interrupt the available fault current. Consult with an electrical engineer to perform a fault current study to determine the available fault current at the transformer secondary. Fuse versus circuit breaker selection is also something to consider. Fuses and circuit breakers are both acceptable overcurrent protection devices, but they have different characteristics. Fuses are generally faster acting and provide better short circuit protection, while circuit breakers can be reset after a trip. The choice between fuses and circuit breakers depends on the specific application and requirements of the electrical system. Proper labeling and documentation are necessary to stay in compliance. Clearly label all overcurrent protection devices with their amperage rating and purpose. Maintain accurate documentation of all calculations, equipment specifications, and installation details. This documentation should be readily available for inspection and maintenance purposes. Regularly inspect and maintain overcurrent protection devices to ensure they are functioning properly. This includes visual inspections for damage or corrosion, as well as testing to verify their trip characteristics. Establish a regular maintenance schedule and keep records of all inspections and maintenance activities. When making any changes or modifications to the electrical system, always consult with a qualified electrical engineer or electrician to ensure that the changes are safe and comply with all applicable codes and regulations. Obtain necessary permits and inspections before energizing any new or modified electrical equipment. Here is a summary of the crucial steps. Firstly, determine the transformer's secondary current rating using the formula provided earlier. Secondly, calculate the maximum allowable overcurrent protection by multiplying the secondary current by 1.25. Thirdly, select overcurrent protection devices, such as fuses or circuit breakers, with ratings that are below the calculated maximum. Fourthly, ensure that the secondary conductors are properly sized to handle the transformer's secondary current, referring to NEC tables for ampacity ratings. Fifthly, verify that the overcurrent protection devices have an adequate interrupting rating for the available fault current at the transformer secondary. Sixthly, comply with all applicable NEC and local codes and regulations, consulting with qualified professionals as needed. Seventhly, properly label and document all equipment and calculations for future reference and maintenance. By adhering to these guidelines and best practices, you can ensure that the transformer secondary is adequately protected, promoting electrical safety and code compliance. Also, consider using a multi-pole circuit breaker or a fuse disconnect switch. These devices provide a single point of disconnection for all phases of the transformer secondary, which can be beneficial for maintenance and safety purposes. A multi-pole circuit breaker will trip all poles simultaneously in the event of an overcurrent, while a fuse disconnect switch provides a visible break in the circuit. When selecting a multi-pole circuit breaker or fuse disconnect switch, ensure that it has an amperage rating and interrupting rating that is suitable for the transformer's secondary current and available fault current. Additionally, consider the enclosure type and environmental conditions when selecting these devices. Also, think about the impact of voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, use conductors with adequate ampacity and keep conductor lengths as short as possible. Calculate the voltage drop in the transformer secondary conductors to ensure that it is within acceptable limits, typically no more than 3%. In addition, consider the use of harmonic filters. Transformers that supply nonlinear loads, such as electronic equipment, can be subject to harmonic currents. Harmonic currents can cause overheating, reduced efficiency, and premature failure of the transformer. To mitigate the effects of harmonic currents, consider using harmonic filters. Harmonic filters are designed to reduce the amplitude of harmonic currents, thereby improving the performance and reliability of the electrical system. Regular thermographic surveys can help to detect hotspots and potential problems in electrical equipment, including transformers and overcurrent protection devices. Thermographic surveys use infrared cameras to measure the temperature of equipment surfaces. Elevated temperatures can indicate loose connections, overloaded circuits, or other problems that require attention. Perform thermographic surveys on a regular basis and address any issues that are identified promptly. Before working on or near electrical equipment, always de-energize the equipment and verify that it is de-energized using appropriate testing equipment. Follow lockout/tagout procedures to prevent accidental re-energization of the equipment. Only qualified and trained personnel should perform electrical work. Also, ensure that the grounding system is properly installed and maintained. A properly installed grounding system provides a low impedance path for fault currents to flow back to the source, which helps to protect personnel and equipment from electrical shock hazards. Inspect the grounding system regularly to ensure that it is free from corrosion and damage. Test the grounding system to verify its effectiveness. It is important to verify the transformer nameplate data. The transformer nameplate contains important information about the transformer's characteristics, including its kVA rating, voltage rating, impedance, and winding configuration. Verify that the nameplate data is accurate and consistent with the electrical system design. Use the nameplate data to calculate the transformer's secondary current and select appropriate overcurrent protection devices. Review the single-line diagram of the electrical system to understand the configuration of the transformer and its associated overcurrent protection devices. The single-line diagram should show the location of all transformers, circuit breakers, fuses, and other electrical equipment. Use the single-line diagram to verify that the overcurrent protection devices are properly sized and coordinated. Check the ambient temperature rating of the overcurrent protection devices. The ambient temperature rating is the maximum temperature at which the overcurrent protection device can operate without derailing its amperage rating. If the overcurrent protection device is installed in a high-temperature environment, it may be necessary to derate its amperage rating. Consult the manufacturer's specifications for derating factors. Also, ensure proper ventilation for the transformer and overcurrent protection devices. Transformers and overcurrent protection devices generate heat during operation. Proper ventilation is essential to prevent overheating and premature failure of the equipment. Ensure that the transformer and overcurrent protection devices are installed in a well-ventilated area and that there is adequate clearance around the equipment for airflow. Consider using forced air cooling if necessary. Also, use surge protection devices to protect the transformer and overcurrent protection devices from voltage surges caused by lightning strikes or switching events. Surge protection devices divert surge currents to ground, thereby protecting the equipment from damage. Install surge protection devices at the transformer primary and secondary, as well as at any sensitive electronic equipment connected to the electrical system. Be aware of coordination studies. A coordination study is an engineering analysis that determines the optimal settings for overcurrent protection devices to ensure that they operate in a coordinated manner. A coordination study can help to minimize downtime and prevent nuisance tripping of overcurrent protection devices. Perform a coordination study when designing or modifying an electrical system with multiple overcurrent protection devices. Lastly, use the correct type of overcurrent protection device. Different types of overcurrent protection devices are available, each with its own characteristics and applications. Use the correct type of overcurrent protection device for the specific application. For example, inverse time circuit breakers are commonly used for motor protection, while instantaneous tripped circuit breakers are used for short circuit protection. Consult the manufacturer's specifications and NEC guidelines for selecting the appropriate type of overcurrent protection device. Remember that electrical codes and regulations are constantly evolving. Stay up to date on the latest requirements by attending training courses, reading industry publications, and consulting with qualified electrical professionals. By staying informed, you can ensure that your electrical systems are safe, compliant, and reliable.